So this is lesson 5 from unit 5. It's our second to last lesson for this particular unit. And we're going to be looking at the fundamental theorem of calculus again. And strangely enough, on our second day of looking at the fundamental theorem, we're actually going to be doing part 1 of the fundamental theorem. Part 2 is the one we did in the last lesson. It's the one that's the most commonly used. And now we're going to catch the other half. We're going to catch part 1. And it's still talking about this idea of accumulating area underneath the function. It's a little story that happens in that process. And so I'm just going to imagine we've got out to this point right here where maybe we're at a particular x value that we might just want to call x. We're like, okay, we got to there, and we've been accumulating area under this graph for some time, right? So we've got this function a of x that's been saying, okay, since the beginning, since some agreed upon starting point, how are we doing for gathering up area? There are times when we don't gather up very much area as we walk to the right, and then there are times when this function gets really big and we gather up area at a really aggressive rate, which is kind of what this part of the fundamental theorem is all about. So we've been gathering up area in here. Let me just officially label this. We'll say, okay, that gathering of area, that function is called a of x, right, as we gather area up. And what's interesting is we're going to look at what happens when we go for just another short little walk, just slightly to the side, and say, okay, in this small little walk that we're going to add, as we go from here to there, just a tiny little addition to our x, we'll call that dx. We're going to go and we're going to gain a little bit more area. We'll call this dA, just a little growth to the area that we've got so far. I'm just going to shade that in here, right? So this is, oh, that's a little thick. 1 second here, I'll try something a little bit lighter. So we're just kind of gathering up a little bit more area. And we know that that height of that function there is going to dictate exactly how aggressively we gather the area up. Now, the actual value of the function right now, we might be up at some point where you've got an x value of x and a y value of f of x. And what we said last day was this extra little ribbon of area that you've gathered as you move to the right, we'll call that dA. It's really just a rectangle, and it would be f of x tall, so the height of the function at that current moment really decides how tall that ribbon would be, and then multiplied by dx for how wide it is. And we talked last time about how you could go and just move this dx differential under the left side of the equation, and you could say this, which kind of says everything right here. It says the rate at which we're gathering up area, the rate at which this green gathering of area grows, is entirely dictated by how aggressively tall the function is at this moment. Well, I just want to take this notion of a of x, this gathered up area, and I just want to officially write that, right, as this definite integral. And then I'll put a derivative out front. So just what I've highlighted there in orange, that part right there, we would say, well, that's officially called the definite integral from 0 in this case out to x, wherever we're currently stopping, of f of x dx. Okay, we've been gathering that up, but in front of that is a derivative. It says, okay, well, sure, that talks about your gathering, and this derivative out front to the left of that says, let's talk about how quickly that gathering is changing. And apparently, it is exactly equal to the height of the function. So the height of the function at this moment just dictates how quickly we're going to be changing that area so far, that highlighted green part. So here's the official rule. First of all, this only works nicely if the function is continuous. So we've seen that issue run all the way through the course. Nice connected graph. Then you could say this. If you were to take a derivative, if you were to ask how quickly is this changing, right? And then you ask, well, how quickly is what changing? Well, how quickly is this integral changing? I don't really care whether you've started at 0, whether you started at 5. You could start at any constant for that matter. So I'm just going to put a constant in here. I'll call it a. And then we're going to go and stop at some sort of stopping variable. I'm going to call that x. And we're integrating this function, right, f of x. Now you can actually put any variable in here, and I'm going to deliberately do that just to emphasize that this is what we call a dummy variable. It doesn't really matter what you put here as long as it shows up right here as well. So often for this rule, we'll put it in just to emphasize that it could go there. That value, the derivative of how fast the integral is changing, is just exactly equal to the current height of the function. So what does this look like to just kind of operate this process? If you ever catch yourself being asked to do a derivative of an integral, those are reverse processes. Those are inverse processes. So kind of like squaring and square rooting, how they undo each other. This is going to undo each other, and you can end up just taking this value here, this x, and just dropping it right into the machine, right? It just goes into that function f, and you're done. There's really not much more to it. The only catch is this number here has to be a constant. And if it's not, well, then we've got to play a couple little games in order to get the rule to be in play. So we're going to try this out a few times. At the beginning, for the first example, what I'd like to do is just one time only, just kind of prove why this works. And then after that, I don't want to do this complicated process again, but I just want to show you why this is indeed true, why the derivative of an integral is going to get you right back to where you started. So here we go. We're asked to do a derivative of this integral of f of w dw. Notice they've got that kind of random variable there. They got w in there. I don't really care about that. That's not going to bother me. You'll see why in a minute. One thing to check, we do have a constant here, so that's actually a good thing. Okay, that kind of makes me happy. Things are going to work out really well. Okay, well, let's go through this process one step at a time. This is going to be painful. We'll do it just once. My first step is to go and do this integral, and then second step, I'm going to go and do the derivative. So first step, let's go and get the integration done. We're going to try to integrate from 0 to x, this thing, f of w dw. Well, that f of w is 3 w squared plus 2w's plus 1. And I'm supposed to integrate that dw. Okay, no problem. I saw last day that I can actually just do an antiderivative, and then I'd be all good to go. So I'm going to do an antiderivative of that purple function that's there. I could go with w cubed plus w squared plus w, and just to throw caution to the wind, how about I throw on there, just for fun, a 14. I want to show you that it makes no difference what constant you put there. And then we're going to go and evaluate that. We've got the starting and stopping spot from 0 to x. And we always go with the final evaluation, subtract the initial evaluation. And now I have to go and put x's into the story and then zeros into the story. And when I do that, I'll end up creating this. I'll end up creating, when the x's go in, I'll have a x cubed plus an x squared plus an x plus a 14. Okay, great. And now I'm supposed to subtract what happens when I put 0 in. 0 cubed, 0 squared, 0, and the 14. So no matter what I tried to put in there to be sneaky, like this 14, it's gone. It's going out of there. And I'm sitting here after the first step staring at x cubed plus x squared plus x. And now what I have to do, the second step in this story was, okay, it's time to go and do a derivative. That was what was sitting up front of this math question. So the final obligation is that you go and do a derivative of this stuff that you found by doing an integral, right? By doing an antiderivative. So you have to do a derivative of x cubed plus x squared plus x. And guess where you're going to end up? You're going to end up staring at the same function we started with, but now it doesn't have w's in it anymore. It's got x's in it. It's 3x squared plus 2x plus 1. It's the same basic thing that we started with, back here, but the w's are out and the x's are in, and that's why we like to write this as just f of x. So really, you're right back to where you started, but any dummy variable is going to come out, and that variable up in the integration, the x in this case, is going to go in. So I want to just kind of show you 4 examples of what it looks like to operate that. It's actually really quick to do, and the first one's kind of just straightforward, and then the next 3 are all the possible things that can go wrong, and then we'll practice one last AP exam question. So this one here. I notice that I'm being asked to do a derivative of an integral, and I know that those two processes are opposites of each other, right? So you don't have to do this, but I'm just going to highlight that operation there is the inverse of this operation. So they're just going to undo each other, and I'm going to get right back to the function that I started with on one condition, and that is that the number sitting right here is a constant. Okay, so I'm going to get right back to where I am. I know that the derivative of an integral is going to get me right back to where I started. So just doing this story over here on this left-hand side of the question, I'm done pretty fast. That's going to end up being nothing more than 1 over, I'm just rewriting this. That's all I'm doing. But I'm not going to put a t in there. I'm going to put this variable that I see right there into it. So it'll be 1 over x squared plus 5. There, I just did the derivative of the integral. And now they've got one more request. They're like, hey, now that you've done that, you wouldn't mind evaluating that answer at 4, would you? No problem. I already know what the derivative of that integral looks like. I don't mind putting 4 in. So this would just be 1 all over 4 squared plus 5, which you could leave like that, or you can say, that's 1 over 21. Okay, they're literally that quick and easy, right? As long as you've got a nice constant down there in the bottom. This one, pretty much the same story. We're being asked to do the derivative, right? They're like, go find g prime. And you're like, okay, well, what's g? G is an integral. So those are going to undo each other. I'm a little bit bothered by the fact that the integral goes from x to 5. So as I stare at it, it looks to me like the numbers there are kind of backwards to what I would expect, to what I would prefer. Talking about the 5 and this x right there. Okay, well, not a problem. Bit of a backwards integral. How about we do this instead? How about we say, well, this g of x, another way to write that, how about we write it forwards? How about we say, no, is it possible to write this integral from, instead of x to 5, how about we write this thing from 5 to x? And it'll be an integral of m squared dm. They've chosen to use that for their dummy variable, whatever. Well, those integrals are not exactly the same until I go and put a little minus sign on it. Because when you integrate backwards, you pick up a negative sign. So there's the new question, right? They're saying g is this integral of m squared. I'm not actually going to go and integrate m squared because I'm about to go and do a derivative of it. They've now asked me, okay, right after that, they're saying, hey, can you go and do a derivative of that? Sure. So g prime, okay, the derivative of this integral, well, the derivative and the integral are just going to undo each other. I do have a constant sitting down here now, so this is good. I'm just going to end up with the same function, that m squared function, except it won't have m's, it's going to have x's, and this minus sign will persist, it'll hang around. So this is actually just negative x squared. It's that simple. I'm just going to highlight this again, if I can find another highlighter color. How about pink? Like right in here, I'm just right back to where I started. I'm right back to that m squared, except now it's x squared. Yeah, there was a bit of a complication with the integral going backwards, but that's okay. And then again, they've got this request. They're saying, hey, you wouldn't mind, would you, just when you're done, when you found out what that derivative looks like, can you go and do a little evaluation? Can you go and do g prime for -7? Sure, yeah, no problem. That would just be the negative of -7 squared. Oh, okay, -49. Done. So if the integral's just mixed up backwards, not a problem. We can switch it around and throw a minus sign in there, and then we're fine. Okay, 2 more. Example 4. Let's see if we can come up with a plan here. Couple things I'm noticing. I'm asked to do a derivative of an integral, so this should be pretty simple. I've got a constant sitting right here. Okay, that's good, because it's supposed to be a constant, so that's great. And then one minor problem. It looks like right here, I've got some algebra. A little more complicated than just an x, but I got a plan. I'm going to go with the chain rule. Okay, here goes. I'm being asked to do that derivative of that integral. It's literally like this. Okay, I'm going to say, okay, if I'm supposed to do a derivative with respect to x, how about we do a chain rule here? How about we do a derivative of that with respect to that algebra blob? I mean, Leibniz would write it officially like this. He would say, why don't we do a derivative with respect to x squared? In other words, let's fake it and just go with the x squared being like x. And I see this integral from 3 to x squared. And then I've got my fourth root of t squared plus 8 dt. I'm going to do that. So this is me just kind of faking this pattern with the chain rule, saying, well, yeah, let's do a derivative with respect to that blue blob. We'll just fake the pattern, which is actually remarkably simple. It says just take that blob, that x squared blob, and just go and drop it in here for t. Just right where the t is, just go ahead and drop it in. But that's cheating, so right afterwards, you have to go and complete the chain rule and multiply your answer by the derivative of the blob with respect to what you should have done. Well, that's remarkably easy. So the plan, next time you might not even write that line down. You might just look at it and go, oh yeah, derivative of an integral, and you got a constant on the bottom, here we go. And you just rewrite the function. So I'm going to go fourth root of, now they had a t squared, maybe I'll just leave this as like a bracket, squared plus 8, and it is literally this quick. You go, okay, what are you dropping in there? Well, they had that blob that I've highlighted in blue. So you'd say, okay, yeah, I'm going to have to put that in. I'm going to put an x squared in right there. I guess it's x to the fourth by now. And then I fix it. I go, oh, okay, well, that was cheating. So I have to multiply by the derivative of x squared, which would be a 2x. Done. Last one. This is as messy as it can get. It says, okay, would you mind doing a derivative of an integral? So I am noticing that I've got these inverse processes going on here. There's a derivative and there's an integral. They're going to undo each other. But they've got this thing, there's no constants in it, right? As it goes from x to 4x squared. My thought on this, what we could do is we could split the integral. Let's break this up. Let's say that h of x is actually done in a couple of parts. We'll get to the derivative in a minute. We'll do the prime thing in a minute. But instead of going from x to 4x squared, how about we go from x to, now, it really makes no difference as long as this is a constant. No difference at all. You could even pick a number. You could say, wow, my favorite number is 3. And you could say, all right, I'm going to integrate from x to 3. This thing right here, w plus 1 dw. As long as right away you kept going and said, all right, I'm going to go from 3 to 4x squared. So I'm assuming that 3 is somewhere in between x and 4x squared. Well, even that doesn't really matter as long as it's not going to bust this function. It could be anything. So if you'd prefer, you could just put a for a constant there. Be totally okay. So I'm going to split h up like that. And then I notice this first integral is a little bit backwards. So I'm still just getting ready to go. And I could say, okay, all right, this is like the opposite of an integral that goes from this constant to x. Any constant you want there. Go ahead and put k in for constant if you want. Be fine. And then this one, the integral from 3 to 4x squared. Oops. Jumping the gun here a little bit. Okay, now I'm going to go and do my derivative. Here comes my answer. I'm going to go and do h prime. Well, as I do a derivative, it's just going to remove that integral sign. And I'm going to end up dropping that x, in this case, into the machine. It's just going to drop in. In this case over here, got a little bit of a chain rule going on. But essentially, this is just going to go into that function. So my answer, it's going to look like this. I'm going to have a negative sign that I've introduced here just to get this problem to work out well. And then I'm going to have the square root of x plus 1. Moving on down the road, I've got this one. Square root of the 4x squared goes right in where the w is. Then add 1. Hey, that one was cheating, just this one. So I'd have to multiply by 8x. Just that one there. Okay, that'd be the only one that needs a little bit of help. So really, it's just a case of dropping in that variable as long as it starts with a constant. Yeah, you might have to do a chain rule in there in order to get everything to be okay. So those are taken care of. This last example goes over a couple of pages, and it's actually an old AP exam question. And we're going to kind of look at a strategy for how to attack these questions. So they gave you a picture on the exam, right? This one's a whole bunch of line segments there, right? Great, 1, 2, 3 different line segments. And they've said, okay, considering that graph of the function f, right? So this is f that they've given us a picture of. Let's talk about a new function, g, that's going to be the integral of f. Well, a couple things I'm noticing right away. G is some sort of chipmunk nut accumulator, like we talked about in the last lesson. And the nice thing is that this chipmunk seems to be starting its accumulation right at 0. Now, I'm just going to pause the video for 2 seconds and come back with a little chipmunk from last day. Okay, we're back rolling again. Grabbed a little copy of this guy from last day's notes. So you can imagine that G is telling the story about this chipmunk that's gathering up area, like gathering up nuts under this graph. And it looks like that chipmunk's going to start right there where I've dropped him, okay, starting at x is equal to 0. And it's going to then go and gather up, you know, stuff underneath that graph, you know, kind of like this, like gather, 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 gather. And at any moment, we could stop and ask, hey, chipmunk, how you doing? So, you know, G at 1 would be asking, hey, chipmunk, how much did you gather by the time you got to 1, when you went from 0 all the way to 1? And when we do these questions, I'm going to show you how you can set up a nice little legend that will really, really help you out. Okay, so let's actually do this right now. There's lots of room up here at the top of the page. The tricky thing is that this picture is not G. The picture that you've got right here is what they're calling f of x. And then G is the story about the chipmunk gathering up area underneath f of x. So I'm going to make a little legend here and see if I can figure out how f and g are related. And I'm going to drop in actually 4 different columns. There we go, that should do. Okay, so they're telling me that g of x, according to their instruction right there, is an accumulator of f. You have to integrate f in order to figure out how big g is. So yeah, okay, this is going to be an integral, and I'm gonna actually write it as f of x dx. Whether you said x or t in there makes no difference at all. Now let's start taking derivatives as we move to the right. So if I take a derivative of g, okay, obviously that's just going to be g prime. Fantastic. But what if you take a derivative of an integral? Well, that's been today's lesson. The derivative of an integral, you're right back to where you started. That would actually just be back to f. So the moral of the story, in the questions that are coming up, if they ever ask me something about g prime, right, the derivative for g, the derivative of this chipmunk success, I know that that's just the picture, right, because f is the picture in this story. Okay, well, maybe they might ask me about g double prime. No problem. That would actually just be f prime. Okay, well, that would be the slope of the picture. Now, I don't think they're going to do it, but if they ask me about g triple prime, I would know what to do. I would know where to look. I would go and look at the picture and look for its second derivative. So that would be the picture's bend, right? Its concavity, the flex of the picture. And that's going to be the legend that I'm going to run to all the time, because they're going to ask me questions about g, and now I know where to go and look. I know how to interpret the picture to help me get there. Okay, here comes the first pair of questions. And for these accumulation questions, often the first couple of questions are the hardest. They want you to find g of 4 and g of negative 2. Okay, so let's just think about what this g of 4 is actually asking. They're saying, all right, if you were to put a 4 in, you know, into this function right here, that means the 4 has to go in there. We're integrating from 0 to 4. So the first part of question A says, okay, if this chipmunk starts accumulating under this picture and goes all the way until they can get to 4, which would stop them there, what's their answer going to be? Well, that's a good question. It's going to take me a little while to figure that out, right? To figure out how much area there is there exactly. To do that, I might even need to find out the equations of these lines. It's not a super quick process, but nothing about it is horribly hard. There is a neat little effect that's going to happen here. The area that gets accumulated from 2 to 3 is actually going to get neutralized, get canceled out by the upside down area from 3 to 4 when you do an integral. So that little bow tie, that feature there is going to totally cancel. So really, what I need to do is just concentrate on integrating from 0 all the way out to 2. I'm just going to find the area under that graph from 0 out to 2. Now, to get there, I might need to think about, what this equation of this line is, right? To think about the slope, so I can actually grab some y values here. Clearly this y value is 4, but what's the y value right here at the start of that picture? It might not be super obvious. It looks like this graph goes 1, 2, 3 over, and then 1, 2, 3, 4 up. So the slope of this graph here, right here, looks like the slope is 4/3. Not a terribly nice number, but that's what it seems to be. Okay, so if that's 4/3 for its slope, here we are at 0 y value. This would be 4/3. That would be 8/3, right? And 9/3 would be 3, so we're a third short there. Okay, so if they want us to figure out, hey, what's g at 4? This is a tough question, right? It's like asking the chipmunk, how many nuts did you gather? How much area did you gather on your journey from 0 all the way to 4 underneath this graph of f of x dx? Well, I'm going to break that up into 2 parts. I'm going to say, okay, why don't we figure out the area gathered up from 0 to 1, a little trapezoid going on there. And then we're going to go from 1 to 2. I'm not even going to bother going from 2 to 4 because I know that that part is 0. Right? So there's like another 0 added on the end from that little bow tie feature that's there. All right, so I need to spend some time and think about how much area there is underneath this graph. It's a trapezoid. So I'll have to sit there and slowly chip away at this answer. It looks like there's a rectangle with a triangle on top, or you could do the average height thing. Okay, lots of options there. I got some room. Maybe I'll scribble this right here. If I was to average 10/3 with the height here, well, we're up at 4. That's like, what is that? 12/3. So we're going to average 10/3 with 12/3. Sorry, I said that a little bit wrong. I don't know why I said 10. We're averaging 8/3 and 12/3. Right, 8/3 for this part of the trapezoid, 12/3 for that one for the 4. So that's an average height of 10/3, and it's 1 wide. So just 10/3 tall on average times 1 wide. This first area here is a 10/3. Now this next part, this one might be a little bit nicer. What's the average height of this trapezoid that's here? I mean, this is 1 tall and that's 4 tall. So if we average those, right, averaging, taking the numbers up and dividing by 2, we were to go and say, okay, what if we were to average 4 and the 1 and then divide by 2? That's 2.5 tall. So that could be written as 5/2. And then nothing, no area for that little bow tie. Well, you're going to need to use sixths in order to get a common denominator here. You could use your calculator if you want, but by the time we go into sixths, this is going to be, 20/6, and this is going to be 15/6, so the grand total is 35/6. Bit of a challenging question there, right? Because you had to think about this accumulation from that little chipmunk trying to gather up all the area like we were joking about in the last lesson. Okay, well, they've got one more, and also a hard one, g at -2. Okay, so we're going to have to integrate starting at 0, going backwards. Be careful, backwards integrals can often be negative. This f of x dx. Got to figure out what that's going to look like. Well, let's go up to the picture and see if we can see how that will feel for the little chipmunk to go back to -2. If I was to sort of highlight the chipmunk's job, starting right here at 0 and then going backwards like that, we're going to ask the chipmunk, hey, how much area did you get? Well, it's a backwards walk for a good function. So it's a positive height to the function, but a negative walk. Okay, so for that part right there, it's going to be the exact opposite of the integral from 0 to 2, right? Because of that backwards walk. So some people like to think of it like this. They'll say, well, that's the opposite of the area that we see from -2 to 0 when we walk kind of in that conventional direction, in that forward direction. Finding the area of that triangle shouldn't be too bad. It's just a triangle. Let's go look at it here. It's 8/3 tall and 2 wide. So for triangles, we're going to go 1/2 base times height. Got a negative sign, so negative 1/2. The base for that thing is a 2, and then the height is 8/3. So it looks like the answer to this one is going to be 8/3. I think that part A, which is often the easy part of an AP Calculus question, I think that's the hardest part to this question. I think it actually gets easier now. Part B says, hey, would you mind finding the instantaneous rate of change of G? Well, I kind of know what that phrasing's all about, right? When they say instantaneous rate of change of G, well, they want you to go and find G prime, right? That's asking you to do a derivative. But a derivative of what? Well, a derivative of G. They want you to go and find G prime at x is equal to 1. That's their desire, right, for you to go and do that. Now, a hard way to do that is to sit there and go, wow, that would be so hard because look at G. This function G is actually tremendously complicated. It's the story about some little algebra chipmunk gathering up area. Now we got to do a derivative of that. But it's actually really nice because we've already set up our legend way back up here. And we've said, based on the fundamental theorem of calculus, that the derivative of G is just the picture. It is just f of x. You do nothing but look at the y values right off of the picture. Not even the slopes of the picture, just the y values of the picture. So when they say, hey, can you do G prime of 1? They're actually asking you to do nothing more than this. Just go and do f. Plain old f of 1. In other words, can you go and just look at the picture value at 1? Just rip off the y value. So you go and you look at the picture and you go, yeah, what is the y value when you're at 1? Oh, 4. Done. Just totally done. Super easy to do, but you had no chance of doing that without some knowledge of some calculus. Okay, let's try out a couple more questions. The backside's the same picture. Okay, the exact same picture, just there as a courtesy. Says, oh, let's go and find the absolute minimum value of G on this closed interval. And then you have to justify your answer. Well, if I'm going to go for the absolute min or max on a closed interval, I know there will be one there. The extreme value theorem says there will be one. I know my plan for doing absolutes, right, if that's what they want. I'm going to go and I'm going to check a couple of things. I'm going to go and check critical points. And I'm going to go and check my endpoints in the story. That's what I have to go and find. So first of all, let's go and get the critical points. Right? So if we're trying to find a critical point for G, then that would be when G prime is either 0 or broken. Okay, well, let's think that through for a minute. Right? G prime. Hey, that's just F. That's just plain old F. So yeah, if you're trying to do a critical point for G, you're wondering, is that ever 0? Is it ever busted? Because you could have maximums or minimums hide there. Okay, well, it's just the picture. So is the picture ever hitting 0? Or is the picture ever busted? Well, the picture itself isn't busted at all from -2 all the way up to 4. It's fine. But it is 0. It's hitting a y value of 0. I'm talking about the picture right there at 3. So yeah, I've got this interesting point to go and check at x is equal to 3. So that's the interesting critical point. Now I'm going to go and check all the possible points. And so it's just a case of thoroughly going through all of these. I should check my endpoints. I should go and check G at -2. I should go and check G at 3, and I should go and check G at 4, and just find out how much area has this thing gathered at each one of those, and then they want the absolute minimum. That's their desire. Okay, so we just have to come up with those numbers, and then we'll be totally done. Well, we've actually already done a couple of these. We did them on the previous page, right? So in part A, we actually found G of 4, and we found G of negative 2. They're totally done. So we can go and steal those answers. The G of negative 2 was negative 8/3. Okay, finished. Okay, just already done. And G of 4, we figured that one out too. I think we got 35/6 or something like that. Already done. Okay, well, they wanted to know also about this G of 3, or we want to know about G of 3 to see how that looks. Well, let's go and look and see what G of 3 would be like for the chipmunk, because we haven't done this one yet. We've done one similar, but not quite this one. So G of 3, the chipmunk starts at 0, according to the story, gathers up area, and apparently we're going to stop the chipmunk at 3. Now we've already done the stopping at 2. Remember we said the bow tie would cancel? Well, this time we're going to go out to 3 and then not include that little triangle from 3 to 4. So the only thing that I think we need to go and focus on is like how much more area is there in here, and then that would have to add to our story that we worked out on the first page. That is just a tiny little triangle. Looks like it's got a base of 1, height of 1, right? And so you'd go 1/2 base times height. So I think the answer for that one, just based on our work on the previous page, this one would be 35/6 plus that tiny little triangle, okay? That little segment that didn't get included yet, because we weren't even looking at it when we were saying, oh yeah, the bow tie just cancels. And so this would be 35 all over 6 plus 1/2. Oh, okay, well 1/2 is just 3/6. So how about if we go and add 3/6 to this, we could say, yeah, 38/6 or 19/3. So if you want to talk about absolute minimums or absolute maximums, I think we're in a good position. I can see them both right here, actually. They wanted the absolute minimum. Well, it was actually this negative 8/3 answer. There's your absolute min. And if they wanted it, this is the biggest number I've seen right here. There's your absolute max. So it's kind of like what we've done before, but we're bringing in this idea of the legend between the two functions, between f and g. Okay, last question of the day, and this actually goes really fast. Even though it's a part D section of an AP Calculus question, usually those are hard, this is going to be pretty quick. It says the second derivative of g is not defined at x is equal to 1 and x is equal to 2. Let's just go and see why that's true for a second. I'm going to go back to my legend. They're starting to talk to me about the second derivative of g. And so in my mind, I'm starting to look over here on this little legend. I'm saying, okay, second derivative of g. Okay, well, I can go and look at the slope of the picture, right? Just the tangent line slope of the picture, and that'll tell me everything I need to know about the second derivative of g. So, okay. So what did they say? The second derivative of g. Okay, the slope of the picture is not defined at x equals 1 and x equals 2. Let's see if that's true. Oh, yeah, totally. You know, at x is equal to 1, right here, I don't know how to draw a tangent line in. No idea. And at x is equal to 2, same thing. Like, how would you draw a tangent line in? Not sure at all. So, yeah, I'm gonna take those little goofy tangent lines out of there and say, yeah, I agree with you. There is no tangent line at 1 and at 2. So sure, yeah, the second derivative of g, not defined there. How many of these values are x coordinates of points of inflection for g? And then you have to justify your answer. This is actually pretty easy to do. It goes like this. If you've got an inflection point for g of x, that goes hand in hand double-headed arrow here with the idea that g double prime, the derivative of the derivative, the second derivative of g, must change sign. In other words, it's got to go from a positive value and then change to a negative value. Or maybe the second derivative goes from a negative value and then changes to a positive value. That's what's going to have to happen if we're going to say, oh yeah, there's an inflection point. Okay, great. But it's really hard for me to think about the second derivative of g. But I've got this plan, right? I can go back again to my little legend if I need to and say, okay, the second derivative of g, that's just f prime. That's the slope of the picture. So it looks like another way to say this is you could say, oh, you want to talk about the second derivative of g? Looks like the slope of the picture. Okay, in other words, f prime of x, slope of the picture, that's got to change sign. It's going to have to do that same thing. It's going to have to go from positive to negative or from negative to positive. Same story, so I'm just going to cheat and put that right there. So all I have to do now is just look at the picture and ask myself, well, at either of these two spots they're talking to me about, does the slope of the picture change sign? All right, well, let's go look. So the contenders are here, okay, at this point and at that point. So does the slope of the picture change from plus to minus or minus to plus at any of those? Well, it does at one only. Okay, only at one of them, and that's at x is equal to 1. It goes from a positive to a negative slope for the picture, but not at x equals 2. It's a negative slope and a negative slope. So I would say, yep, I can see it. It's going to happen only at one of them. Okay, so just only at x is equal to 1. Moral of the story with these ones, set up that legend, right? So I'm just going to go back to the very beginning here when they first started saying, oh yeah, the function g is a bit complicated. It's actually going to be some sort of little gathering of area, like a chipmunk gathers nuts, for the graph of f. Okay, so you can set that up, then start taking derivatives. And then you're ready to go. And if they want to start asking you about the second derivative of g, you're like, no problem. That's just the slope of the picture. If they want to talk about the derivative of g, you can just say, no problem. That's just y values on the picture. If they want to talk about g, which was actually part A, that's hard, actually. You got to go and physically do the little gathering of the area, right? Think about the little chipmunk gathering nuts like we joked about in the previous lesson. And that finishes up our second look at the fundamental theorem of calculus.